Good day, ladies and gentlemen. My name is Imran Khan, and I will be presenting our topic on a sustainable approach to the construction of coastal facilities through the incorporation of beach sand and brackish water in concrete production. Water is a major component in concrete production, and Trinidad and Tobago is one of the 7 Caribbean nations considered to have extremely high levels of water stress by the World Resources Institute. Regions experiencing high levels of water stress can benefit from this approach to concrete production. Aggregate is typically mined from alluvial deposits, which is a non-renewable natural resource, due for its demand from many sectors such as civil engineering, manufacturing, and tourism. Consequently, new sources must continually be discovered and evaluated for purpose. Use of on-site aggregate for coastal construction projects improves the sustainability prospects for construction in these environments. Traditional concrete reinforcement made of steel are particularly vulnerable in chemically aggressive environments such as coastal areas. This ultimately has an effect on the durability of such concretes. The introduction of polymeric reinforcements in coastal construction projects can increase the lifespan of these coastal structures. With these considerations in mind, our research was aimed at examining the prospects of utilizing beach sand and brackish water in concrete production and initiating open discourse on the use of non-metallic reinforcement in concrete structures. Our methodology can be split into 5 areas. This slide examines our concrete mix designs used. 22 batches of concrete were made according to ACI standard 211.1, using water to cement ratios which ranged from 0.37 through to 0.45. For each mix ratio, the design mix was varied as follows. The fine aggregate was either concreting sand or beach sand. The mixed water used in the cement mix was either fresh water or brackish water, and the water used for curing the concrete mix was either fresh water or brackish water. The combinations of fine aggregate, mixed water, and curing water used in concrete mix design are as follows. Concreting sand as the fine aggregate, fresh water as the mixed water, and fresh water as the curing water. This concrete mix design was designated by the code CFF. The first letter of the concrete mix designation represents the aggregate, either C for concreting sand or B for beach sand. The second letter represents the mixed water used, either F for fresh water or B for brackish water. And the third letter represents the curing water used, either F for fresh water or B for brackish water. Other variations used were concreting sand as the fine aggregate, fresh water as the mixed water, and brackish water as the curing water. We also used beach sand as the fine aggregate, fresh water as the mixed water, and brackish water as the curing water. Concreting sand as the fine aggregate, brackish water as the mixed water, and brackish water as the curing water. And lastly, beach sand as the fine aggregate, brackish water as the mixed water, and brackish water as the curing water. The other 4 areas in our methodology were testing of aggregate, testing of water, setting times of the cement mixed with fresh water and brackish water, and compression testing of the concrete. The aggregate was tested for organic content and a sieve analysis of the fine aggregate was conducted. The coarse aggregate was supplied by a ready-mix concrete company and as such met the required ASTM criteria. The fresh and brackish water used were tested for salinity and ion concentrations of sodium, potassium, magnesium, and sulfate. Looking at the organic content, we see that the organic content of both the concreting sand and the beach sand were in the color range of 1 and 2 respectively. This falls well within the acceptable range of 1 to 3, indicating that beach sand is suitable as a fine aggregate based on its organic content. In the sieve analysis test, the fineness modulus of the concreting sand was 2.7, whilst the natural fineness modulus of the beach sand was 1.9. This value was too low for use with the ACI 211.1 standard. Thus, it was separated and reconstituted to a fineness modulus of 2.6. Salinity tests showed that the brackish water had a salinity of 5.65 parts per trillion, which falls within the acceptable range of 0.5 to 35 parts per trillion for brackish water. Table 1 shows the breakdown of the chemical analyses performed on the freshwater and brackish water. Note that the brackish water contained approximately 10 times more sulfate ions and 4 times more sodium ions than the freshwater, while the potassium and magnesium ion content were comparable for both freshwater and brackish water. These low concentrations of potassium and magnesium ions suggest that the majority of sulfates were associated with sodium ions. The initial setting time of the brackish water was only 4% shorter than for the fresh water, a difference of only 5 minutes, and the variation in final setting time for brackish water was only 2% greater. Thus, there was no significant acceleration or retardation of the setting process by using brackish water. On to compression testing. Figure 4 shows the variation of compressive strength with water to cement ratio after 7 days. The CFF series generally produce the highest 7-day strength, with CFF 37 producing the highest strength of 38.7 megapascals. The lowest 7-day strength amongst the batches was with the BBB 41 designation at 20.4 megapascals. As is expected, we notice the general trend is toward a reduction in strength with increasing water to cement ratio. Figure 5 shows a similar graph but after 28 days. The BBB 37 series produced the highest 28-day compressive strength at 40.4 megapascals. Again, the lowest strength observed was with the BBB 41 designation at 24.9 megapascals. The majority of batches did not meet the 28-day design strength as prescribed for a target mean strength. Exceptions to this were the BFB 43, which was designed at 39 megapascals and tested at 39.6 megapascals, and CBB 45 and CFB 45, both designed at 37.5 megapascals and tested at 37.9 megapascals and 40.9 megapascals respectively. At 42 days, we see a similar trend in the reduction of compressive strength with increasing water to cement ratio. Generally, strengths did increase over the 28-day values, with most of the batches reaching the 28-day characteristic strength at 42 days. On completion of this phase of our research, the following conclusions can be drawn. Fine aggregate is a non-renewable resource essential to many industrial sectors, and therefore evaluation of possible alternative sources for applicability is necessary. Sometimes this may involve adjusting the fineness modulus. Beach sand produces stronger concrete with brackish water, however, offshore sand may be superior. Coastal construction projects are ideally suited to make use of the excavation soil. However, special permissions may be required to excavate beach sand. The use of brackish water in concrete production lessens the impact concrete production would have in water-stressed areas. And long-term investigations are required to investigate the durability of concrete produced with newer materials and from exposure to seawater. This marks the end of our presentation. Thank you.